Is my screen visible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So let us quickly recall what we did yesterday's lecture, uh, Thursday's lecture. You started with a series expansion of a function in ascending powers of x. Okay. So there are two series expansion. First is Maclaurin series expansion, and second is Taylor's series expansion. Okay, in which Maclaurin series expansion is series expansion about zero. Okay, that means at zero, and Taylor series expansion it is at any point a that we are going to study later. So the statement says that if f of x is differentiable function, n time differentiable function, then we can expand it in ascending powers of x as f of 0 plus x into f dash 0 plus x square by 2 factorial f double dash at 0 and so on, plus x raised to n upon n factorial nth derivative at 0 and so on. Okay, note that it will not stop at this step. Okay, x raised to n upon n factorial fn at 0. Okay, it will continue after that also. This is the general term. All right. And after that we considered one problem to find out series expansion of sine x, and we observed that it is x minus x cubed by 3 factorial plus x raised to 5 by 5 factorial minus x raised to 7 by 7 factorial and so on. Okay, so please note down this series expansion because we are going to use it uh, in further problems. Okay, so similarly we can obtain series expansion of following functions. So write down cos x. So it is 1 minus x square by 2 factorial plus x raised to 4 by 4 factorial minus x raised to 6 by 6 factorial and so on. Okay. Note that here denominators are factorial of odd numbers, whereas in cos x denominators are factorial of even numbers, and alternate plus minus in uh, plus minus sign are there. Okay. So in similar line, you can obtain series of tan x, which is x plus x cubed by 3. Okay, this is not factorial. It is x plus x cubed by 3 plus 2 by 15 x raised to 5 plus 17 by 315 x raised to 7 and so on. Okay, idea is same. You find out f of 0, that is tan 0, then its derivative at 0, then second derivative at 0, third derivative at 0 and so on. Okay. E raised to x is 1 plus x square by 2 factorial plus x cubed by 3 factorial and so on. Then sine hyperbolic x, of course you don't know hyperbolic function, but right now you write it as sine hx. Okay, there is a special type of function in complex theory, and those are called as hyperbolic functions. So sine hyperbolic x uh, is different from sine x. Okay, you can check that this is x plus x cubed by 3 factorial plus x raised to 5 by 5 factorial and so on. Okay, everywhere there is positive sign, whereas in sine x there is alternate plus minus. Okay, please note the difference. Similarly, cos hyperbolic x is also 1 plus x square by 2 factorial plus x raised to 4 by 4 factorial and so on. All are positive. Okay, whereas in cos x alternate plus minus and is plus and minus is there. Then tan hyperbolic x is x minus x cubed by 3 plus 2 by 15 x raised to 5 minus 17 by 315 x raised to 7. alternate plus minus is there, and you can check that in tan x it is positive everywhere. X plus x cubed by 3 plus 2 by 15, x raised to 5, and so on. Okay, so note the differences. Then next is series expansion of log of 1 plus x, which is x minus x square by 2 plus x cubed by 3 minus x raised to 4 by 4 plus x raised to 5 by 5, and so on. Okay, so you can obtain series of log of 1 minus x from this above series. Simply replace this x by minus x, you will get series of log of 1 minus x. Okay, so if you replace x by minus x, you will get minus x square by 2 minus x cube by 3 and so on. Okay, now if you differentiate uh, this log of 1 plus x, so its differentiation is 1 upon 1 plus x. By mistake that ma'am has written this 1 minus x. Okay, it is 1 plus x. Now if you differentiate term by term, you will get 1 minus x plus x square minus x cube and so on. Okay, so this is a series expansion of 1 upon 1 plus x. This is plus 1 upon 1 plus x equal to 1 minus x plus x square minus x cube and so on. And if you differentiate 9, then its differentiation is 1 upon 1 minus x into minus 1. Okay, 1 upon 1 minus x into derivative of minus x is minus 1. So, and if you differentiate term by term here, you will get minus sign out, 1 plus x square plus x cube plus x raised to 4 and so on. So minus sign will get cancelled from both sides. So series expansion of 1 upon 1 minus x is 1 plus x square plus x cube and so on. Okay. Any doubt so far?
No, sir.
No, sir.
Okay.
Sir, can you scroll up for some time? I was not
Yeah.
able to write some of those.
Okay, fine. Write it fast. Please remember that these are not formulae. Okay, you can actually obtain this series expansion. Done.
So you said there was some mistake in one of those.
This
Can you
tenth
repeat
tenth
that?
one, tenth one.
Yes, sir.
Differentiate 8. So differentiation of log of 1 plus x is 1 upon 1 plus x. So this is 1 plus
This
x.
plus.
Yeah.
Yes, sir.
And lastly, there is binomial expansion. 1 plus x raised to n is equal to 1 plus nx plus n into n minus 1 upon 2 factorial into x square plus n into n minus 1 into n minus 2 upon 3 factorial x cube and so on. Okay. So this is again useful in some problem. So please note it down. Can we go ahead?
Yes, sir.
Okay. What about others? Have you copied?
Yes, sir.
Yes, sir.
Yes, sir.
All right. So let us go to the example. Uh, First is expand 1 plus sine x uh, up to x raised to 6. Okay. Now, in each of the example, you are going to use standard expansions of a function. Okay. So here there are two choices. Okay. First choice is 1 plus x raised to n. Okay. This is binomial expansion. So 1 plus sine x raised to half. Okay. So 1 plus sine x raised to half, that will be 1 plus n into sine x plus n into n minus 1 upon 2 factorial sine x bracket square and n into n minus 1 into n minus 2 upon 3 factorial sine x bracket cube. Okay, and so on. And then you substitute series of sine x. So 1 plus n into series of sine x, then this factor into sine x ka sine x series and its uh, square, and then again its cube, which becomes complicated for further calculation. Okay, so I suggest you to don't go for 1 plus sine x raised to half using binomial expansion. Okay, and there was a trick for this problem. You write down this 1 as sine square x by 2 plus cos square x by 2, and this sine x as 2 sine x by 2 cos x by 2. Okay, so this will become cos x by 2 plus sin x by 2 bracket square. Okay, So you will get rid of this square root. So cos x by 2 plus sin x by 2. Now this x by 2 is say y. Okay, x by 2 is y. So cos y plus sin y. So you want its expansion. So cos y ka expansion is 1 minus y square by 2 factorial plus y raised to 4 by 4 factorial and so on. Then plus sin y ka expansion y minus y cube by 3 factorial plus y raised to 5 by 5 factorial and so on. Okay. Just note that they have asked you to find out series expansion up to x raised to 6. That means it is mandatory to find out coefficient of x raised to 6. Okay. You can't just find out coefficient of x raised to 5 and then dot dot dot. It's not allowed. Okay. You lose your marks. You have to find out coefficient up to x raised to 6. Okay. So there should be one more step in this cos x, and what that should be? This x by 2 raised to 6 upon 6 factorial. Okay, that term has to be there. All right, up to this step, any doubt?
No, sir.
No, sir.
What about others?
No, sir.
Sir,
No,
can
sir.
you once again tell why we can't use 1 plus x raised to power n?
See, 1
Also, n
plus
should be integer there, so it cannot be
no no no
half.
no 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 no. N can be a real number. That is fine.
It will be too long
Yeah.
because we are using two expansions at once.
Yeah, good. So here it is x ki jagah sin x, and that too series of sin x. Here sin x ka square. That means you need to write series of sin x and square it. Again here series of sin x and then cube, and then
Yes,
you
sir, got
collect
it,
the
got it.
coefficients. That will be very much critical.
Yes, sir, got that.
Yeah. So this was the trick for this problem. Okay. So then you write x by 2 as y, and then you expand it as cos y plus sin y, and then you resubstitute your y as x by 2. So series of cos x by 2 is 1 minus x by 2 square upon 2 factorial plus x by 2 raised to 4 upon 4 factorial minus x by 2 raised to 6 upon 6 factorial. Okay, this term is there because you have asked to find out up to x raised to 6. Then you can write dot 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 because next term is x raised to 8. All right. Then plus series of sin x by 2. So x by 2 minus x by 2 cube by 3 factorial plus x by 2 raised to 5 by 5 factorial. And next term is x by 2 raised to 7, which we don't want. So that you can skip. Okay. Now collect the constant term. So constant term is 1. Terms of x is x by 2 only. Then terms of x square. So here it is. So x square by 4 into 2. Okay. So 1 by 8 into x square. This is 1. Okay. 1 by 8 into x square. Then terms of x cube. So it is 1 by 8 into 3 factorial. That is 6. So x cube by 48. Do you understand what am I doing? I'm writing.
Yes, sir.
Yeah, I'm writing in ascending powers of x. Isn't it?
Yes, sir.
Okay. And then x raised to 4. So 1 by 2 raised to 4, that is 16 into 4 factorial. That turns out to be 384. Then x raised to 5. So 1 by 2 raised to 5, that is 32 into 5 factorial. That will be 3840. And then lastly, this is 1 by 6 factorial into x by 2 raised to 6. Okay. So that coefficient is 1 by 460 80. All right. So just note it down.
Sir, at the last, shouldn't it be minus x to the power 6?
1 minus plus minus. This has to be minus, right? Correct. Very good. Done. Can you go ahead?
Yes, sir.
Okay. What about others? Have you copied?
Yes, sir.
Okay.
I think, sir, 1 minute.
Which step? Last or second last or third last?
Last step, last step.
Okay.
Done, sir.
Okay. So second is expand log of 1 plus x square plus x cube up to x raised to 8. Okay. So again, there are two choices. Log of 1 plus this whole thing. Okay. And that will be treated as a y. 1 plus x cube plus x square plus x cube is y. But again, that calculation becomes too lengthy. Okay. So there is a simplification here. So 1 plus x, and here you can take x square out. So that becomes x square into 1 plus x. So log of 1 plus x into 1 plus x square. And you simply distribute log. So log of 1 plus x plus log of 1 plus x square. Up to this step, any doubt? Yes?
No, sir. No doubt.
No, sir.
Okay. Now, once you have this log of 1 plus x and log of 1 plus x square, you have series expansion of log of 1 plus x. And that is x minus x square by 2 plus x cube by 3 and so on. And here also, you can write this x square as y. So log of 1 plus y, that is y minus y square by 2 plus y cube by 3 and so on. Okay. And later you substitute y as x square. Okay. So let us see. So log of 1 plus x is x minus x square by 2 plus x cube by 3 minus x raised to 4 by 4 plus x raised to 5 by 5 minus x raised to 6 by 6 plus x raised to 7 by 7, and there is one more, minus x raised to 8 by 8. Okay. Last, because you have asked to find out up to x raised to 8. So there is one more step, one more term, minus x raised to 8 by 8 plus x, that is x square, minus x square by 2, so x raised to 4 by 2 plus x raised to 6 by 3 minus x raised to 8 by 4, and then you can write dot dot dot. Okay, because we want up to x raised to 8. And then secondly, collect the coefficients So coefficient of x is 1, so x as it is. Then coefficient of x square, so here it is minus 1 by 2 plus 1. Okay, here it is minus 1 by 2 for this term, and here it is plus 1. So it becomes minus 1 by 2 plus 1, 1 by 2. So x plus x square by 2. Then coefficient of x cube, here it is 1 by 3, and here there is no term of x cube. So x cube by 3 as it is. Then coefficient of x raised to 4, here it is minus 1 by 4 and minus 1 by 2. Minus 1 by 4 and minus 1 by 2. So that becomes minus 3 by 4. Then coefficient of x raised to 5 is 1 by 5. And here there is no term of x raised to 5. So x raised to 5 by 5. Then coefficient of x raised to 6 is minus 1 by 6 here and plus 1 by 3 here. So that becomes 1 by 6. So x raised to 6 by 6. Then x raised to 7 by 7. Okay, and there is no term of x raised to 7 here. And at the end, here minus x raised to 8 by 8. So minus 1 by 8 minus 1 by 4. That becomes minus 3 by 8 x raised to 8. All right. And that is series expansion up to x raised to 8. Any doubt? Yes, any doubt?
No, sir.
Okay.
No, sir.
Please note it down. Done? Can you go ahead?
Yes, sir.
Others, please respond.
Yes, sir.
Yes, sir.
Okay.
Sir.
Clear, sir.
So third is expand 1 plus x raised to x in ascending powers of x. So what we'll do in this expansion is we'll apply log, and then we find out series expansion, and then we take exponential on both sides. Okay, I repeat, let us apply log on both sides. So we'll have expansion of log y at the end, and then we take exponential on both sides. So e raised to log y will become y, and then here some series. Okay, so y is equal to 1 plus x raised to x. And
Sir,
yes,
should also be expanded, right?
which one? Which one? Sorry.
It's x log 1 plus x, right? So, sir, so x should also be expanded, right?
There is no expansion of x. X is the single term because we are writing in ascending powers of x.
Okay, sir.
So apply log on both sides. So log y equal to x into log of 1 plus x. So you know series expansion of log of 1 plus x, that is x minus x square by 2 plus x cube by 3 minus x raised to 4 by 4 plus x raised to 5 by 5 and so on. Okay. Now you have asked to find out up to fifth power of x. Okay. So you can write up to x raised to 4 or x raised to 5. Okay. Now this x is in multiplication. So multiply it. You will have x square minus x cube by 2 plus x raised to 4 by 3 minus x raised to 5 by 4 plus x raised to 6 by 5 and so on. Okay, so this is log y ka expansion. Now out of which I want y, so apply exponential on both sides. So e raised to log y equal to e raised to this series. Okay, and that series we call as a z. Okay, this series is some term, some function z. So y is equal to e raised to z. Up to this step, any doubt? Is it fine?
Yes, sir.
Okay. Now e raised to z, again this is exponential function whose standard expansion you know. So that is 1 plus z square by 2 factorial plus z cube by 3 factorial and so on. Okay. Now you substitute this z. So 1 plus z is x square plus minus x cube by 2 plus x cube by 3 plus x raised to 4 by 3 minus x raised to 5 by 4 plus x raised to 6 by 5 and so on, plus 1 by 2 into z square. Okay, so this series ka square. Okay, and then plus 1 by 6, that is 1 by 3 factorial is 1 by 6 z cube. So x square minus x cube by 2 plus x raised to 4 by 3 bracket cube. Okay, cube is missing here. Fine. Now let us collect the coefficient. What is constant term? 1. Okay. What is coefficient of x? Tell me. Coefficient of x. Is there any term of x?
0.
0. Okay.
No term of x, sir.
Right. Coefficient of x square. Where is x square? X square is here only. Okay. So the x square as it is.
By 6.
Sorry.
Coefficient of x square, sir, 1 by 6.
7 by 6. Why?
1 by 6, not 7 by 6.
Why 1 by 6?
But after taking the LCM of both expansions,
No, here is x square and there is nowhere x square. See, this
There's
is
a
a square.
cube on the third.
This is square and this third term is cube. Okay, x square minus x cube by 2 plus x raised to 4 by 3. And this bracket cube is there. She has missed to write it.
okay, sir.
Okay, so there is only single term of x square. So 1 plus x square as it is. Then x cube ka coefficient. What is it? Where is x
It's 1
cube?
by 2.
Yeah, it is minus 1 by 2.
Yes, minus.
Minus 1 by 2. And there is no x cube here and here also. Okay. See, while looking at x cube, I am also considering powers. Okay. Because in this expansion, there is no term of x cube if you square this. Okay. Therefore, x cube ka coefficient is minus 1 by 2. This is plus, but actually it is minus. So minus x cube by 2. Then coefficient of x raised to 4. Yes. Tell
1
me.
by 3.
5 by 6.
This 1 by 3 and if you open this x square minus x cube by 3 bracket square, what will be first term?
X raised to 4 upon 2.
X raised to 4 upon 2. So 1 by 2. So 1 by 2 plus 1 by 3. What is it?
5 by 6.
5 by 6. Okay. So 5 by 6. Then coefficient of x raised to 5. What is it? Here it is minus 1 by 4. Then
1 by 6.
1 by, this is minus 1 by 4. Where we'll get x raised to 5? Here. Okay. A minus b, for time being you consider first two terms, x square minus x cube by 2 and bracket square. What is it? X square minus x cube by 2 bracket square. If you consider first two terms and if you square it, so x raised to 4, then second term x raised to 6 minus 2 times ab, right?
Yes, sir. So, and
So-
considering the half which is outside, minus half will be the coefficient.
Yeah, and if you add them, you will get minus 3 by 4, right? Right?
Yes, sir.
Yeah. What about others?
Yes, sir.
Yes, sir.
Yes, sir.
So everybody understand that coefficient of x raised to 5 is minus 3 by 4. Okay. And let me tell you that in exam, what exactly we are going to check are the coefficients. Okay. At the end, if you substitute series expansion correctly, then we are going to check these coefficients of powers of x. If they are correct, then your whole calculation must be correct. Okay. So just note it down. Let me scroll up so that you will write it.
Sir, could you scroll up to the question?
Okay.
Thank you, sir.
So
Yes.
I have one question over here. Like we are this series, all these series are infinite series. Like
Yeah. Correct.
they don't sum to infinity, but they are till infinity. So
Yes.
there are certain laws of like dealing with infinite series. Otherwise, if we are just adding them like normal integers or something like that, then the Ramanujan's proof of like sum of infinite number is something negative number.
Negative number.
So
Okay.
that would be like correct, and which is not correct. So are there any exceptional rules over here which we are just not known yet?
For certain series, there are some rules like for this 2. Okay. There is expansion of 1 upon 1 plus x is 1 minus x plus x square minus x cube and so on. This is true if and only if modulus of x is less than 1. Okay, that means x should lies between minus 1 to 1, And similarly, here also series expansion of 1 upon 1 minus x is 1 plus x square plus x cube and so on. Then this series expansion is true provided mod x is less than 1. Okay, that is the only assumption one has to consider. Otherwise, all other expansions are true for x. Okay.
Okay, sir, got that.
Yeah. By the way, what is the statement of that Ramanujan's the theorem you are talking about? Do you?
Sir, I don't. I have actually done that 2 3 times, but I don't remember exact the whole scenario. But it was like he has taken some series, he has added one in it, and he has subtracted one from that series, and the series was just the same. So series minus one is equal to the series. Then on that basis, he made the further calculations.
Okay. And what was the sum? What was the sum of that series?
Sum was a negative number, sir. It was like I don't remember the exact number. It was minus 11 by something, I think so.
Minus
I
1
don't
by
remember.
12.
Minus 1 by
Yes,
12.
minus 1 by 12. Minus 1 by 12. Exactly.
1 plus 2 plus 3 plus 4 plus 5 and so on. Some of these infinite numbers, it has to be divergent series because there is no finite sum for this series. And using Riemann zeta function, he
Yes,
has
sir. Riemann
proved
zeta
that,
function. Exactly.
yeah, he has proved that it is minus 1 by 12. Okay. For that calculation, there are some constraint. Okay. Under that constraint, that series expansion is minus 1 by 12.
Yes, sir.
So, but then are we allowed to take the exponential if we are dealing with such sums?
Yeah, yeah. Domain of exponential function is whole real line, no?
So, because then the exponent will not be actually defined, right?
In this case, it will be defined. What is the problem? Tell me.
So then if we are getting an infinite series, then we cannot actually say that the exponent is actually defined.
Oh, you mean this Z?
Yes, sir. When we are
Yeah,
taking
yeah.
e raised to z.
Okay, you mean this has to be some convergent series. This should converge to some number.
Yes, sir. Then for it to be placed on the real number series, we should have it to converge.
Yeah. But right now we are not worrying about these numbers which we are placing to x, okay? Because we are writing it general as x. So if we are writing it as e raised to z, that means there are assumptions that, okay, this series is convergent for some numbers x, okay? And that will be our domain. Okay, so we are not
Sir,
worrying about values of x which we are going to substitute.
and I also had a doubt that when we are taking say anti-log on both the sides, then for log or anti-log, the
Again,
thus the
question
domain
is,
is also defined,
yeah,
right?
yeah. Again, question is same that which values of x we are dealing with. So we are writing that x as general or variable x, but again, when we write e raised to z or log of something, we are under the impression that for that value of x it is true. Okay. Otherwise, this series expansion is not possible for any function.
Okay, sir. So it is approximation considering that we
For
know the exact value of x.
yeah, right. For certain value of x, wherever it is true, for that value we are dealing with.
Okay, clear, sir. Okay.
Yeah. Okay, just copy it fast. It's 9:20. If you are done, just let me know. Uh, Here it is minus x cubed by 2. Huh? Make a correction. This is minus x cubed by 2. Unfortunately, before writing a series, one should know about convergence and divergence of series. Okay, then and only then these questions can be handled. Are you getting my point?
Yes, sir.
Yeah, and that is
Yes,
not
sir.
there in syllabus. But there is a topic in engineering mathematics, convergent and divergent series expansion. Okay, there they talk about when series will be convergent and what will be actual sum in certain cases, and when it will be divergent. There they are defining range of x. Okay, for these values of x, it is defined or it is convergent to some number. Otherwise, it is divergent. Okay.
Sir, so I have a doubt, sir. Then how do we define it for the hyperbolic trigonometric functions? Because they are divergent.
Hyperbolic trigonometry. No, no, no. They are not divergent. Okay. So if I take x is equal to 1, forget about this sine hyperbolic 1. Okay. If I take 1 plus 1 by 3 factorial plus 1 by 5 factorial plus 1 by 7 factorial, and if you study series of uh, study convergent series, okay, separately, if you study convergence of this series 1 plus 1 by 3 factorial plus 1 by 5 factorial and so on, okay, whatever value you will get, that will be same as sine hyperbolic 1.
Okay, sir. So we compare them.
Yeah, and that will happen for any value of x. Therefore, series expansion of sine hyperbolic x is this.
Okay, sir. So for all of these expansions, we actually cannot do the expansion because series, we cannot find series because divergent, but we find similar series and compare it to them.
Compare it, right? That's what he has done. Maclaurin's okay. He has done this calculation: f of 0 plus x into f dash 0 plus x squared by 2 factorial and so on. Okay. Then considering one function f of x. Okay. Then he calculated sum of this side. Okay. Sum of this side, right hand side, and he checked that the same number is there on left hand side if you substitute that value here. For example, if you take series expansion of e raised to x to right hand side, and if you substitute x is equal to say 0, so that sum was 1. Similarly, if you substitute x is equal to 0 to the left hand side, that will be e raised to 0, again that is 1. All right.
Okay, sir. Got it.
Therefore this statement came out.
Okay, sir.
Yeah. Fine. So have you copied this? Can we go ahead?
Yes, sir.
Okay.
Yes, sir.
So this is the trick. Anyway, so I just want to hide this, but it is displayed. This is interesting. Uh, Series expansion of tan inverse x. Okay, and it is x minus x cubed by 3 plus x raised to 5 by 5 minus x raised to 7 by 7 uh, and plus x raised to 9 by 9 and so on. Okay. Interestingly, if you try it on your own without this technique of differentiation, it is difficult because x raised to 9 means how many coefficients you are supposed to find, how many derivatives you are supposed to take. Yes, if you are actually using Maclaurin's theorem, how many derivatives you
Nine
will have to
times.
take? 9 times you will have to differentiate. Okay, and which becomes a tedious job. Okay, so do you understand what am I saying?
Yes, sir.
Yes, sir.
Yes, sir.
There are two ways to find out series expansion of tan inverse x. One is using actual definition, okay, and second one is using differentiation and integration. So first way is to find out 9 derivative, and then you find its value at 0, okay, which is time consuming. Probably it will take more than 45 minutes, 40 to 45 minutes. But here, if you differentiate it, y is equal to tan inverse x, its differentiation is 1 upon 1 plus x square, okay, and what we know is there is expansion of 1 upon 1 plus x is 1 minus x plus x square minus x cube and so on, okay. Now you, in place of x, you substitute x square, so dy by dx is equal to 1 minus x square plus x raised to 4 minus x raised to 6 plus x raised to 8, okay. So this is series expansion of dy by dx. I want series expansion of y. What should I do?
Integrate.
Integrate, okay. So integration dy by dx is with respect to x, that is y. So integration of 1 is x. So this is x cubed by 3, x raised to 5 by 5, x raised to 7 by 7, and so on, okay. So this is a trick. In fact, you can use this trick for many of the inverse trigonometric function. To find series expansion of inverse trigonometric function, you will use this trick. All right. So it's 9:28. We'll continue with this next time. Before leaving, just note down your name and roll number in chat box.
Done, sir.
Yeah. So any doubts so far?
No, sir.
Yes, sir.
Okay. Okay. So see you next time then.
No, sir.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you, sir.
sir.
Thank you.
Thank you, sir.
Thank you.